All right, good day, one and all. So we are continuing with week 6 lab activity. Good. So what are we doing in week 6? Now we are doing oxidation, reduction, titrations, and then we are doing mainly KMNO4 titration. So titration involving potassium permanganate. Okay. Now the first thing we'll learn how to do is how to standardize KMNO4, and then we determine the purity of ferrous sulfate crystals, and then we determine the volume strength of hydrogen peroxide. Very simple. Good. Now the first one, general information about KMNO4 titration. So we are seeing that KMNO4 is one of the most powerful oxidizing agents available. It is usually used in acidic solutions when employed in titrimetry for analysis of substances. Now, KMNO4 is very powerful. I think it's among the most powerful examples I have in my head. So it is part, and then usually you have chromic acid, right? Yes, and then you have, this is also a powerful oxidizing agent, that is nitric acid, right? You can find more examples of very powerful oxidizing agents. Good. Now we are seeing that we use the KMNO4 in acidic solution. Now we are using acidic solution because it has so many reasons, but then because in acidic solution, the oxidizing power of KMNO4 is increased. That is the first thing, that in acidic solution, the oxidizing power of KMNO4 is increased, and then usually we want to prevent the formation of what? Of MnO2, which is the brown color. You want to prevent the formation of MnO2, which is the brown color, right? If there's no acid, you realize that the reduction will take us to Mn4 plus instead of taking us to the Mn2 plus, right? So we add acid so that we can prevent the formation of MnO2. Good. The last thing we can see is that the acid becomes a catalyst to the whole reaction, right? It becomes a catalyst to the whole reaction. So that is that for that. Now we are seeing that in acidic solution, the reaction with reducing agents can be represented by, so we have the ionic equation here, the MnO4 minus ion changing to the Mn2 plus ion, right? That is the actual transformation. This is the purple color, and then this is the colorless or the faint pink color, right? Good. Now, we are saying that the manganese ion is so intensely colored that although indicators are available, it can serve as its own indicator. Very simple concept, that the KMNO4 has color, right? Because the color is very intense, we use itself as an indicator. So we call it a self-indicator or an own indicator, right? We don't need to add any other indicator to the titration. KMNO4 change color to show the endpoint of the reaction, right? Usually in this titration, we ask what indicator is used. Some people might say no indicator. What is wrong, right? There's an indicator. The KMNO4, it's a self-indicator, right? Good. The manganese ion produced as so faintly pink, and then has to be virtually colorless. So sometimes you see this, the Mn2 plus ion is colorless, right? But then ideally it's faintly pink. Now we are seeing that the endpoint in the KMNO4 titration is reached when the faint color that persists for about 30 seconds upon shaking the flask is obtained. Very important point. That when you start your titration and then you drop your KMNO4, right, from the bridge, usually you see a pink color. Now that pink color might persist for like 20 seconds, but that is not the endpoint. The color will go away. Now when you start titrating, you realize that there will be color changes that will diminish within a small period of time if you swell. But then if you have a pink color forming that persists for like 30 seconds, then you know that you have gotten to your endpoint. We are saying that potassium permanganate may be standardized with sodium oxalate or oxalic acid, right? Now we are saying that sodium oxalate is preferred because it is readily available to a high purity, that's 99.95. And unlike the oxalic acid, it can be gotten in the anhydrous state. I think this one should make sense. So we can either use sodium oxalate or oxalic acid, but then we prefer sodium oxalate, the salt, because it is readily available, right? It is readily available, and then we in high purity, and then it can also exist in the anhydrous state, that it can exist without water of crystallization. That is what we are seeing. Now, I think the formation of brown color in the titration is caused by insufficient acid. It means if there's no acid, you form a brown color. That is one important why we use the KMNO4 in acidic solution. And then if the temperature is too high, you also form a brown coloration, right? Then we are saying that if the flask is dirty, can also lead to formation of brown coloration. Good. Now, determination of purity of ferrous sulfate crystal. Ferrous sulfate can be used in treatment of iron deficiency anemia. On standing in contact with air, some oxidation to ferric state can occur. Good. So we are saying that ferrous sulfate can be used in treatment of iron deficiency because of the Fe2 plus the ferrous, right? Now, when you leave the ferrous sulfate, right, the Fe2 plus changes to Fe3 plus. Now, this is the main problem. This is the main problem with ferrous sulfate, it's being oxidized to the ferric state. For each reason, we check the purity to still know the amount of what Fe2 plus inside the drug. Good. Now we are saying that ferrous sulfate crystals are thus assayed to determine percentage purity in comparison to the accepted range or criteria in the British Pharmacopoeia. The ferrous ion is oxidized to ferric state using this equation. So this is the equation showing the oxidation. This is not the full equation. I think this one, you should add 1 mole of electron here to make it balance at this stage. Now, this is the actual reaction between the KMNO4 and then the FeSO4, right? Good. Now, we are supposed to learn the reaction. Ideally, we are supposed to learn how to balance the reaction and all, but trust me, this is the same reaction that will come if they are giving you this question. This is the same reaction that will come. So even if you can't balance it, learn this balanced equation. The most important thing here is that after writing your balanced equation, according to what we have done in the previous week, you need your mole ratios. You state your mole ratios of KMNO4 and then the FeSO4. That is it. Good. Now, that's a typical question for us to go through. We are saying that Kofi prepared a solution of 0.25 molar KMNO4 and standardized it with the primary standard of annular sodium oxalate. Now, the process was carried out in a triplicate to obtain an average titer. And so, always, I said before we do a titration, you do a standardization, and that is what has been captured in the first part of the question. The next part says, in an assay of ferrous sulfate heptahydrate crystals dissolved in solution, Kofi pipetted 25 mL of 1 liter of ferrous sulfate heptahydrate crystals, right? Now, she added sufficient acid to the solution and warmed it up gently over a water bath and titrated against a standard 0.25 molar KMNO4. The result shown below was obtained for the acid. So 3 determinations, right? Good. Now we can find the titer at each level. So this is 18.90. This one here. Let me check it on my calculator. So this is 18.8. And this is also 18.80. So we can find your average titer. Right, let's go through. We'll see the average titer in the solution. Now, these are the questions. We are saying that the first question, calculate the mass of ferrous sulfate present in the 1 liter. Now, from the question, realize that the stock was 1 liter and then we took 25 mL to do our titration. So we can calculate that, right? Then the mass of elemental ion present in the ferrous sulfate heptahydrate and the percentage purity of ferrous sulfate if 130 grams of the powder was dissolved to make 1 liter of the solution, right? Good. So these are the figures given. Very simple. Now we'll use each of these figures as we progress. Now, very important thing here, that is the equation for the standardization of KMNO4. They have not given us the full reaction, but at least they have shown us that the mole ratio is 2:5. Very important. That is what we need from the balanced equation. Right. Now the average titer. So the average titer will be a sum of all the 3 titer values divided by 3. We are getting 18.83. That's the average titer, right? Then this equation has already been given in the slide. The most important thing is that we should know 2 moles of KMNO4 reacts with 10 moles of ferrous sulfate heptahydrate, right? Now we write our standard statement for equivalent calculation. That is, the molar mass of ferrous sulfate heptahydrate in 1000 ml will react with 1 molar KMNO4. Then I correct it with my mole ratio. So this one multiplied by 2, this one multiplied by 10. Good. Then I step the volume down to 1 ml. I step the concentration down to that which was given to me in the question. Good. Now when I get here, it means this concentration, the 0.25 molar of KMNO4, right? 1 ml of it will react with 0.3475 grams of ferrous sulfate heptahydrate. Very simple, right? Good. So this means every 1 ml of KMNO4 released from the bread completely neutralizes 0.3475 grams of ferrous sulfate heptahydrate in the pipette volume of the solution in the conical flask. Now, after getting this, we can just use what we do here is called proportion. We can use proportion to get all our values. So if I want the actual ferrous sulfate heptahydrate in the 25 mils, right? Now, 1 mil of the KMNO4 reacts with this. Then the actual volume of KMNO4 reacts with what? So the actual volume of KMNO4 will be the average titer times the factor. And that is giving me 13.52. 13.52. Now we get the factor from the standardization procedure, and then it was given to us because we didn't do the standardization in this case. Good. So my actual volume is 13.52, and then I'll come and say that if 1 mol of KMNO4 reacts with this, according to a milli equivalent calculation, then the 13.52 reacts with, so it's proportion, right? This and this divided by the 1 mil. And then that will give me 4.6982 grams of ferrous sulfate heptahydrate. Now, this is what reacted with the average titer, right? Now, because I pipetted 25 mils, it means this is the amount of ferrous sulfate in 25 mils. So this is the amount in 25 mils. My next work is to find the amount in 1000 mil or the 1 liter. So if 25 mil corresponds to this one, then 1000 will correspond to it. So I do cross multiplication here, right? And I get 187.920 grams of ferrous sulfate heptahydrate. So this is the amount in the stock. The amount in the stock. Good. Now, the percentage purity would be the actual weight of the ferrous sulfate heptahydrate over the expected weight times 100. So now, the expected weight was given to us in the question. The actual weight is what has been calculated from the experiment, right? And the expected weight was what was given to us in the question, right? So the question made mention of the fact that, let me check. Okay, so that's it. So we measured 130 grams of the powder to make up that 1 liter solution, right? That means the expected amount we measured was 130 and the actual was 187.928. So we divide the actual by the expected and multiply by 100, and then we are getting 144.56, right? Very simple. The next question is for us to find the amount of elemental iron. What is the actual amount of Fe in the mixture, right? Good. And then that will be the atomic weight of the iron over the molecular weight of the compound times the actual weight in the solution. So the atomic weight of iron is 56, right? Divided by the molecular weight of the whole compound times the actual weight in the 1 liter. And that's giving us 37.8560 grams right? So that's the mass of elemental ion. Very simple. Good. So that is that for the first assay of ferrous sulfate crystals. The next one we are doing determination of the volume strength of hydrogen peroxide. When we started, we mentioned the fact that volume strength is a special property or special character of what? Hydrogen peroxide, right? It actually shows us the amount of oxygen that can be liberated by the hydrogen peroxide. So we'll talk about that as we want. But we are saying that hydrogen peroxide is a disinfectant used in the first aid treatment of minor cuts and abrasions, and also as mouthwash. Right, so you can check the mouthwashes on the market. Most of them contains the hydrogen peroxide. Now we are seeing that it is unstable and then decomposes to form water and oxygen. It is always obtained in aqueous solution, the concentration of which is usually quoted in volume strength. Now, if we have 10 volume strength peroxide, it means that a certain volume of the hydrogen peroxide will completely decompose and yield 10 times of the volume of oxygen measured at STP. So we are saying that assuming the volume strength of the peroxide is 5 volume strength, right? It means if you take 2 mL of the peroxide, it will give 2 times 5 of oxygen at STP, the standard temperature and pressure, right? Standard temperature and pressure. So that is that for that. Good. Now we are okay. So this is the equation for the peroxide changing to what? Changing to the oxygen gas, right? Decomposing to the oxygen gas. I think we should take note of this equation, right? Very simple, very simple. Good. Now we are saying that hydrogen peroxide reacts with potassium permanganate in an unusual reaction, resulting in the formation of oxygen, according to this. Now it is because of this reaction, that is why we can do standardization of what on assay of peroxide with KMnO4, because the MnO4 minus can react with the peroxide and then form the Mn2 plus, and that is the faint pink color that we are talking about, right? It means that the KMnO4 can oxidize the peroxide to water, right? And then oxygen gas, and then itself can be reduced to the Mn2 plus ion. So because of this, there will be a color change, and then that color changes from the purple color to the faint pink color. And then for this one, we can use the KMnO4 to assay the peroxide. I hope we are following. Good. So an exercise to that effect. So we are saying that Angela prepared a solution of 0.25 molar of KMnO4 and standardized it with a primary standard solution of annular sodium oxalate. The process was carried out in triplicate to obtain an average titer. During the assay of hydrogen peroxide, Angela took 3 mL of hydrogen peroxide solution, whose total volume was 200, right, and diluted it to 300 with distilled water to produce a solution B. 25 mL of the pipetted solution B was titrated against the previously standardized 0.25 molar KMnO4 solution, and the results are shown. So very simple. Now let's digest the question. This first part of the question is talking about standardization of KMnO4, and as mentioned already in the previous videos, we are saying that we don't use reagents without standardizing them. So standardization, right? Good. Now the next part of the question is giving us the assay of the hydrogen peroxide, and then there are dilutions here that makes the question quite confusing, and then we have to pay attention to the dilutions, right? So the first thing, we had a stock solution of 200 mL. We took 3 mL of that and then diluted it to 300 mL. So that is just the dilution. Then you have a stock of 200 mL, very concentrated, right? You take 3 mL from that stock and then you dilute it to what? 300 mL. Good. So we take part of this 3 mL and then you add water so that you get your 300 mL. And then in the titration, you pick something from that 300 mL, 25 from the 300 mL. And so we're reading that if you find the amount of hydrogen peroxide in the 25 mils, you can do proportion and then find the amount of what? Of the peroxide in what? In the 300 mils, right? Now, after getting the proportion, the 300 mils, because water was just added from this stage to this stage, it means the amount in 300 mils is the same as the amount in the 3 mils, because there was just dilution from 3 to 300, right? And then once you get your 3 mils content, you can just do extrapolation and then get the amount in the stock, which is the 200 mils. So that is just the technicality there. Now, this is the table from the assay, right? Good. So the first question is that we have to find the mass of hydrogen peroxide in your stock. We have to find the percentage weight in volume of hydrogen peroxide. We have to find the volume strength of hydrogen peroxide stock solution. Good. So this is KMnO4, sodium oxalate, hydrogen peroxide. Okay, so they have given out all the values we need. Now, once again, they have given us the equation for the standardization. Even though the standardization is not shown in this calculation, always we do standardization before we do the actual milli equivalent calculation, right? Good. So that is that for that. That is that. I hope we have not forgotten our standardization. Now, the actual assay solution. So we find the average titer, we get 7.53 as always. As always, as we get the same volume, but as always, as we have to find the average titer. Good. And then this is the equation. The equation has already been stated in the slide. The most important thing is that 2 moles of the manganese ion, 2 moles of the manganese ion would react with 5 moles of what? Of hydrogen peroxide. So this is the mole ratio. Very important. Now we write a standard statement of equivalent calculation, and then we correct it using the mole ratios, right? Using the mole ratios. Now, after that, we step the volume down to 1 mil, milli equivalent, and then we step the concentration down to that which has been given in the question. Now, when we get our milli equivalent calculation, we explain that it means that 0.25 molar of KMnO4, if you take 1 mil of it, it's supposed to react with 0.0213 gram of peroxide, right? Good. Then we come here and we say that if 1 mil of KMnO4 reacts with this mass of peroxide, then the actual volume of KMnO4, right, that will be the average titer times the factor will react with what? So if we find the actual volume, multiply the average titer by the factor, we are getting 6.91. And then we come back to our proportion and say if 1 mil reacts with this mass, the 6.91 of KMnO4 reacts with what? So the amount of KMnO4, the amount of peroxide that reacts with KMnO4 has been found here. That is 0.1473 grams of peroxide, right? And then this will be the peroxide in the 25 ml that we pipetted. This will be the peroxide in the 25 ml that we pipetted. Good. Now, after getting the peroxide in 25 ml, we can use that to find the peroxide in the 300 ml by proportion. We are getting 1.7676 grams of the peroxide, right? And this is what we'll have. This is what we will have in the 300 mils. Now you realize that 300 mils was just the final product after diluting the 3 mils. It means the amount of peroxide didn't change, moving from the 3 mils to the 300 mils. So we can see that the amount in the 300 mils is the same as the amount in the stock 3 mils, right? Good. Now, if you are supposed to find the peroxide in the stock, then we'll say that the 3 mils would have this. If the 3 mil has this, then the 200 mils stock will have. So we do another proportion here, cross multiplication, then we get 117.8420 grams of peroxide. So this is the amount of peroxide in the stock 200 mils. In the stock 200 mils, right? Very simple. The next one is asking us to find the percentage concentration or the percentage weight in volume. Now the percentage concentration is the amount in grams over the volume in over the volume in what 100 mils, right? Or the amount of the substance in 100 ml of the solution. Very simple. Now the stock given is 200 mils. And so if 200 corresponds to this amount, 100 ml will correspond to what? Right? Percentage mass over volume says the amount in grams over 100 mils of the solution. So if 200 corresponds to this, then 100 ml will correspond to what? We'll do our proportion and get this. right? Now, the 58.92 grams we have gotten will be a percentage weight in volume. That means if you take 100 ml of the solution, you get what 58.92 grams of the peroxide. Very simple. Now, the last and the most important thing we have to determine here is the volume strength of the peroxide. The volume strength. Now, we state the equation gently or nicely, right? The equation has already been given to us in the question. Now, we state the mole ratio. That 2 moles of peroxide can decompose and give me 1 mole of what? 1 mole of oxygen. Now, we do something else, that we state the mass of the peroxide. It means 34 grams. That is, on a normal day, if you are doing our equivalent calculation, we would have said that 34.0000 grams of the peroxide will react with, or will give us 1 mole of oxygen gas. Now, we are saying that a mole of oxygen gas at STP corresponds to this volume, right? This is basic chemistry. It corresponds to this volume. That is the 22.4 dm cube, or the 22,400 mLs, right? So instead of writing, because you're not interested in the concentration, but we are interested in the volume of oxygen produced, we can just do this extrapolation. So we'll say that on a normal day, per the standard, the molar mass or the molecular weight of the peroxide, right, would give us the standard volume. That's the 22400 mLs of oxygen gas. Now you have to correct this with what? The mole ratio. So I multiply this by 2, and I multiply this by 1. And then I multiply this one by 1. Good. So the molecular weight of peroxide is 34, right? So I'll have 2 times 34, and that will give me the 68, right? And that will correspond to the one standard volume, that is the 22,400 mLs of oxygen gas. Now we are saying that if we have this mass, right, that is the conclusion we are drawing here, that if we have this mass, that is the 68 grams of peroxide, it will decompose and give me this volume, right? Now, what would the weight in 1 ml stock give me? So that is just the meaning of volume strength. Now, from the question, the total amount in the stock, right? We know that the 200 ml contain this, so we have to find the amount in 1 ml. The grams in 1 ml will be gotten by doing cross multiplication at this point, and then we are getting 0.5892 grams of peroxide, right? Good. Now that's the amount in 1 ml. So we can come back to our proportion that we're doing. That is 58 grams of peroxide corresponds to this volume of oxygen. Then 0.5892 corresponds to us. So we'll do another cross multiplication here, and then we get 194 mLs of oxygen gas, right? Now, this 194 mLs of oxygen gas becomes the volume strength of what? Of the peroxide. It becomes the volume strength of the peroxide, such that if you take 1 ml of the peroxide, it will decompose and give you this amount of oxygen gas in mLs, right? It will give you this amount of oxygen gas in mLs. So that is what we are saying here. That is what we are saying here. Very simple. Very simple. So I think that will be the end of the calculation. Now, one thing that we didn't stress on during this video is the procedure. Then if this one will come in exams, you need to know the procedure, right? You need to know the procedure. So do all and go through your lab manual and master the procedure for the titration experiment, and then all the best in your exams. Thank you very much for your audience.